Evening, everybody. 5 o'clock, Thursday night. Time for some Calc 3. So we've got one of our final sections, surface integrals. Excuse me, which we'll talk about surface area a little bit too. And next week is going to be our last week. We have 2 sections next week as well. Most likely I'll cover them both on Tuesday to leave most of Thursday open for any questions. This is the last section that is on the proctored final exam section. So divergence theorem and Stokes theorem, which are next week, won't be on the proctored exam, but they will be on the take-home problems. So plan for today, we're going to go through surface area and surface integrals. I have about 7 examples I want to go through with you guys. And we'll see where we're at after that. We may not have time for group work today just because I really want to spend time on these examples, see what kind of questions come out from them. And excuse me. And that to me is the most important thing. And these problems can take a little bit longer from the worksheet. So, you know, by the time we're done going through examples and everything, if there's not a lot of time left, then we may not do any specific group work today, but we'll see. We'll play that one by ear. All right, so let's dive into this one. We're going to talk about surface area first. We talked a little bit about surface area last time, and we did an example. So I'm going to pick up with surface area and do a similar example. So the idea is basic. You know, if we have a surface in 3 space, we want to calculate its surface area. So last time we were doing parameterized surfaces. And we know that double integrals can be used to calculate area. So they can do the area of some surface that's actually not in the XY plane. So last time we looked at how to calculate the surface area of a parameterized surface, and we're going to refresh our memories on that. So if we have some vector parameterization, all right, this would be, you know, we looked at a cylinder, we looked at a torus, you know, we looked at those parameterizations last time. This could be the parameterization of any of those. The surface area is given by the following formula. We basically do the double integral over the region of the magnitude of the cross product. And the reason this works is because the magnitude of the cross product gives us the area of a trapezoid. And so what we're doing is we're breaking up the surface into infinitely small trapezoids and then integrating over all of those. So that's just a little bit of idea of why this looks the way it does. Basically, our position function is a mapping onto our surface. And so what we're doing is we're breaking up our region into basically what are a bunch of little trapezoids. Again, we turn that into a Riemann sum, and then we do infinitely many of them, and that's what creates the double integral. It's actually pretty cool. Let's look at what this is going to look like in practice. So the surface area of a cone with a height of 1, and I don't think we did a cone, we did a paraboloid. The cone is very similar. If you remember the paraboloid, really the only difference is we squared this last part. I am going to use Maple for some calculations today, and I gave that in more as a handout, and I'll put it in chat here once we start using. Actually, I'll put it in chat now, because I have all the calculations done in here just to save some time. But let's talk about how we would do the cone of height 1. So for that parameterization, here's what our graph would look like. Nothing crazy, just a cone And, you can do surface area of cones with some closed formulas, but we're going to do it with the double integral. So we're looking at the surface area of this region here. All right, let's talk through the steps. So first off, we have our position function, which is r cosine theta, r sine theta, r. And then we need to find basically r of u and r of v, but now I used r and theta in here. So what we're looking at is the partial of r with respect to r. So the derivative of each component with respect to r. Now the derivative of r is 1, so we get left with cosine theta, sine theta, 1. And we're going to do the derivative of r with respect to theta. So derivative of cosine theta is negative sine, so we'd have a negative r sine theta. Derivative of sine is cosine, so r cosine theta, and then 0. All right. Now the next step is to do the cross product of the two. Now again, for time's sake, I've already got these calculated out. They're on the maple sheet that I sent you. And let me bring it over so you can see what I'm talking about. So right here, I kind of walk through it. I do the cross product. The cross product is here, then it's put into the integral. So I'm going to be using this to keep from taking too long with the computations. We know how to do cross product. We know how to do double integrals. What I want to focus on is setting them up. So when you do this cross product, you get negative r cosine theta, negative r sine theta, r. Now, what goes in the integral, so now when we go to calculate the integral, it's the magnitude of this vector, which is the square root of the sum of the squares of the components. Negative r cosine theta squared plus negative r sine theta squared plus r squared. And the limits, and this is what's great about having it parameterized, the limits of integration are the limits you'd have on your parameterization. Well, this cone's at 90 degrees with a height of 1, which means r is going to go from 0 to 1. And theta, to get all around the cone, has to go from 0 to 2 pi. It's one of the nice things about the parameterization. You know your limits on your definite integral. Now, this one I'm going to simplify because we are going to see it again in another example, and I want you to just see how it transfers. So one of the nice things that happens, we're going to end up with, an r squared cosine squared theta here, and an r squared sine squared here. Well, we can factor out the r squared, and we get cosine squared plus sine squared, which just leaves us with r squared plus r squared. So square root of 2r squared dr d theta. And we can actually pull that r out. So we have 0 to 2 pi, 0 to 1, square root of 2 times r dr d theta. So it's actually not a very bad integral to calculate. And you just end up with pi times square root of 2.
I have a question.
Sure.
When we parameterize this, shouldn't it be RD theta? Or is that just not, is it like not the normal polar parameterization?
Right. So good question. So the reason we have to add in R in those other cases is because we are integrating in polar, or yeah, polar since we're in 2D. We're not integrating in polar here. This is actually X, Y, and Z. So we actually are in rectangular, which is why we're not putting the extra R in the integrand.
So we don't have to, like, we're not parameterizing it. I don't know if that's the right word. We're not changing it, though, from one form to another. It's already done for us.
Right. Well, no, it's not that we're not changing it, actually. To be more specific, it's that we're in rectangular, meaning, our parametric equations are X equals R cosine theta, Y equals R sine theta, Z equals R. Versus if our if our parameterization had been in cylindrical, our position vector would have gone R comma theta comma Z. And so actually, this would have been pretty much our parameterization. It would have been a little bit different.
Got it.
Then we would have, in this case, we would have been in polar. Then when we go to set up our integral, we would have had R here. But as you can imagine, our partials are going to look a little different. This isn't quite the right parameterization, but this is the order that it would be in, R, theta, Z. We would have to give those, we'd have to give R and R, theta, and Z in terms of U and V or whatever we want our parameters to be. But because our parameterization is actually in rectangular, we don't need the extra R in there. Okay. So it's actually a really good question.
I think I just thought it was in is it polar? Is that the one that's got RD theta?
Yes.
I just thought it was in polar because it has thetas and R's in it. I think it's where I got mixed up.
Yeah, and we could have just as easily, and I probably should have just had U and V in here because it's what I have in the notation up here. I just happen to have it in terms of R and theta because anytime we're dealing with a cone, it's really easy to do in terms of polar, and these are our polar transformations. But we are in rectangular. That's why we don't need the extra R here.
Okay, thank you.
Other questions about this first example? But yeah, we could have just done U cosine V, U sine V, and V. Sorry, U cosine V, U sine V, and U. I just happen to have it written up this way. Excuse me. All right. Now, this is how we can do surface area if we have our surface parameterized. Let's talk about if our surface is written as a function. All right. So if our surface is given as Z equals some function of X and Y, well, then we can think of our position vector being X, Y, F of X, Y. Then if we did R sub X and R sub Y, we would get the following. And then when we do the cross product on this is just the derivation. This is not something you guys have to do. When you do the cross product, the magnitude of the cross product, it actually boils down to just the square root of F sub X squared plus F sub Y squared plus 1, which you probably saw in the video. So when we have a function this is a way of calculating the surface area. So I want to really stress that we're not doing anything different goal-wise. We're still calculating surface area of a surface. I mean, we could do a cone if we wanted to. We would just have to define it as a function. We could do, you know, we can do it either way, whichever way we find simpler. But sometimes it's going to be easier just to say, okay, well, I've already got the function defined in terms of x, y, and if all I need is the surface area, this will work. So let's do this function here. So this is example 2. So z equals 6 minus 3x minus 2y. That's in the first octant. So here is a plot of what's going on with this one. We're just in the first octant. So we're looking for the surface area basically of this slanted triangle, this blue surface here. Pull that over. All right. Now, here, first off, let's talk about our integral. Well, we're going to need, and since I have it written as z, let's keep it that way. Let's keep our notation consistent. We need our partials. So -3 z sub y equals -2. So as we start to write up our definite integral, it's going to be the square root of -3 squared plus -2 squared plus 1. And now we need to think about our order of integration. So we're integrating over a region R. That region R is our shadow region in the XY plane. We've talked about that a little bit before. So for this particular surface, it's this triangle in the XY plane. We can see it goes through 0, 3 for Y and 2, 0 for X. So that's what we need to set up our limits for. So, and again, this is something you guys have done before. This part's not new. So you can really see how everything it really builds nicely the second half. So we need a linear function between these two. Let's see, we got a slope of -3/2 and a y-intercept of 3. So y equals -3/2 x plus 3. We can honestly do this one in either order, but since my linear function is already written for y, we might as well do dy dx. And so y is going to go from 0 up to the curve, or up to the linear function. So -3/2 x plus 3. And x is going to go from 0 to 2. So we have 0 to 2, 0 to -3/2 x plus 3. And in here, we're going to have 9 plus 4 plus 1. So 14, which is just a constant. So really, this actually ends up being not a bad integral to do by hand. But again, since I already have it calculated, except I moved it. If you guys want to try this one later, it comes out to be 3 square root of 14. All right. So we have two formulas that both calculate surface area. And again, one is if you're doing parameterized surface. The other is if you're doing a function. And in a lot of cases, you can really choose which one you want to do. If we have time to do one from the worksheet, the one I'm going to give you is one that has you do it both via parameterization and do it via the function to make sure you get the same thing. And what I would say is if we don't get time to get to that one in class today, that would be a great one to try over the weekend. So I'll make sure to mention that at the end if we don't get a chance to break into groups. All right, questions at this point? So that's surface area. So the next thing we're going to talk about are our surface integrals, because they're just an extension of surface area. So what we're doing now is integrating a function over a surface. So basically, what we did in chapter 14 is we've integrated functions over regions in the XY plane. And we integrated functions over three-dimensional figures. Now we're going to integrate over a 2D surface in 3 space. So, we'll integrate over, so the examples I'm going to do, we're going to integrate over these surfaces we already saw. Now, just to give us a little bit of context here, what's going on, if our function represented a density, then the surface integral would calculate the total mass of the 2D surface. So that's essentially what's going on. Now we're integrating a function over a surface. And it's not tricky. Basically what happens is we add the function on to our surface integral. So now if I wanted to calculate the surface integral of f of xy equals xy over our previous surface. In fact, we're going to just go back to that slide because we got so much of the work done. Right here was our surface integral. Or excuse me, our surface area. Basically, what we're going to do is we're going to take that and we're going to add the xy in. So, actually, let's even have the r out of the square root. Everything else stays the same. So let's see, we had, I already forgot the limits, 0 to 2 pi, 0 to 1. 0 to 2 pi, 0 to 1, rad 2, oops, sorry, I don't want to do that just yet. Our function, our function in terms of our position vector times basically our surface area, which we saw before came out to be rad 2r dr d theta. So really the only thing I've added in is we have to add in our function, but it has to be in terms of our position vector. Remember that our position vector was r cosine theta, r sine theta, r, x, y, z, and we literally just sub in these for the x's and y's. So our function is x times y. Well, we're going to sub in r cosine theta for x, r cosine theta for y. So let's write this off to the side. So f in terms of r is going to be r cosine theta, r sine theta. Okay, that's using our function here with our position vector as the input. And that's really all that does is that maps this function into this r theta plane. So 0 to 2 pi, 0 to 1. We can simplify, r times r is going to give us an r squared. And we even have this other r here. And I'm going to keep them separate for this line, just in case you guys come back to this. Cosine theta, sine theta, and then we have the rad 2r dr d theta. Okay. Now again, we would multiply those r's together, do our integral in terms of r. If you're doing it by hand, cosine theta times sine theta, we use a quick little u substitution. let u be sine, then du is cosine theta d theta. Again, this I already have calculated. And it comes up to be 1/8 times rad 2. Again, not surprising the rad 2 ends up in our answer because our rad 2 is here. Questions about that? So hopefully you're seeing how this builds, right? We did the surface area. Well, to do the surface integral, we're really just adding in the function in front of it. Now, you know, these integrals can get pretty hairy depending on what your cross product comes out to be and what your function is. And that's why, you know, if you get one of these on the take-home problem, feel free to use technology. I would not give you a nasty one on the proctored exam. But the steps are the same. And that's the part I want you to see. Because if you can set up the integral, we always have technology to help us calculate it. So your job, your main job is setting up the integrals. So that was example 3. All right. Well, let's go on to the next example. And this would be a surface integral over our surface if it's given by a function. All right. So we're going to use the same function as before because we already know that this part just comes out to be rad 14 and we already know our limits of integration. So we're going to integrate over this surface, the 6 minus 3x minus 2y in the first octant. And our function now is g of x of y of z equals x, y, z. Now, it doesn't have to be a function of 3 variables, but I picked this example specifically because I want you to see one thing. Now, let's go ahead and set this up. Again, we already know our region. It's the same as before. So 0 to negative 3/2 x plus 3, and then 0 to 2. We're going to be plugging in our function. But there's one thing we have to be aware of. It's only a double integral. We cannot integrate with respect to z. So that third part is going to be our surface. So instead of putting z here, because I don't want z in there, I can't integrate it, I'm going to put what z is equal to, which is that guy right there. So 6 minus 3x minus y. And that keeps that function in terms of x and y, because z, remember, we're on this surface, so we already have z defined in terms of x and y on the surface. So this is z. It's just defined in terms of x and y. And again, we did this part in example 2. We know that that comes out to be square root of 14. Sorry about that. And we're going in the order dy dx. And now let's just see what this is going to look like when we set it up. And then we'll be ready to compute. Minus 3/2 x plus 3. So we take our function, which is x, y, z. So x, y, and then again, z is going to be this thing right here. 6 minus 3x minus, sorry, that should be minus 2y. Should be a 2 right there. Times rad 14 dy dx. Now, what we would do to solve this, we distribute the x, y. We could pull the rad 14 out front and then do the antiderivative with y, plug in the limits, then do the antiderivative with respect to x, plug in the limits. It's actually not too bad of a one. It's not as bad as it looks once you distribute. All your antiderivatives are pretty basic. What you should get if you want to try this one is 9/5 times square root of 14. Questions about that one? All right, quick recap of what we've done. We've done surface area of both parametrized surfaces and surfaces defined as a function. And we've done surface integrals of a surface given parametrically and a surface given as a function. Now we're going to move into surface areas of vector fields. This is going to be similar to something we did with our line integrals, because now we're going over a vector field. So when we did our line integral over a vector field, that was basically telling us to what extent our path is going with or against our vector field. So if the vector field represents a flow of the fluid, then what happens is the surface integral will represent the amount of fluid flowing through the surface. Now, if you remember when we did Green's theorem, there were two versions of Green's theorem. There was the circulation version, which did the line integral, and then there was the flux version that did the flux integral. That's what we're doing with these surface integrals over vector fields. We're essentially going to be doing flux integrals. Here's the only difference. When we did them with line integrals, when we were working on line integrals, we were doing it over a one-dimensional path. And we were looking to what extent, does the vector field go out of our closed path versus into our closed path. Now we're looking to, and it was a single variable integral. Now we're looking to what extent does the vector field go through our surface in one direction versus the other direction, and it'll be a double integral. All right. So we have done flux integrals. We've only done them in one dimension because we were doing them on a path. Now we're doing them on a surface. So the flux is a term used in physics, and it can be a rate transfer of fluid, particles, energy. So there's a lot of uses for flux integrals in physics. And just to give you kind of an intuitive sense of what's going on, if you imagine water flowing through a surface, if the flow of the water is perpendicular to the surface, a lot of water is going to flow through and the flux will be large. If the flow of the water is parallel to the surface, then no water will flow through and the flux will be zero. So in order to calculate flux, and this is the same thing that the Green's theorem did, is the Green's theorem used the divergence because we needed to get the component that was perpendicular to the path. Now we need the component that's perpendicular to the surface. All right. So we're taking the components of the vector field that are perpendicular to the surface. So let's let n represent some unit normal vector to our given surface. Then in order to find the component of f that is perpendicular, we can do the vector projection between f and n, which is the dot product. This will get us the component of f in the direction of n. N is already a unit. We're already assuming n is a unit vector, so that's why we don't need to normalize it or anything. So it's going to be zero if we know the dot product is zero if they're perpendicular, and positive if they're in the same direction, negative if they're in the opposite direction. Nothing new. This is from all the way back where we started with dot product. It's actually pretty cool how we've come full circle, and we're really starting to use a lot of the vector mathematics that we learned at the beginning of the semester at this point. So given some flow, integrating F dot N will determine the total of flux of fluid through a surface. And it's going to be positive if it's in the same direction as N and negative if it's in an opposite direction. In other words, if you have a surface and you defined an outward and an inward direction, which we will talk more about that. If it's flowing in the outward direction, if it's flowing out of a surface, then we would say the flux is positive. If it's flowing into the surface, we say it's negative. That's the same way we define divergence. And you'll see next week when we talk about the divergence theorem, how that connects to this. All right, so that's what we're going to look at next, is surface integrals over vector fields, which would be our flux integrals. Okay. Now, I'm going to start with a formula here, but we're going to simplify it a little bit. So basically what we're going to do is we're going to combine our dot product with our formula from the surface integral before. We're going to replace the function with the dot product. Because what we want to do is we want to sum up all these pieces over the surface. So I think the idea of this formula is pretty clear. This is going to sum up all the pieces of F that are in the direction of N. And then this is going to integrate it over the surface. But this actually can be simplified. So let me go through that with you just so you can see how we'll see the formula for when we need it in practice. So the formula for a unit normal vector, if we're given a parameterization, comes from the cross product. Remember, the cross product gives us a vector that's normal to the plane that these two vectors lie in. So these give us a normal vector, then dividing by the magnitude makes it a unit normal vector. So if we insert that into our formula, if we replace N with this, we get a cancellation of the scalars. So here's our more simplified formula. All right. So let's see what this looks like in practice. So let's say we have the surface is our paraboloid, z equals x squared plus y squared. We'll just have z go from 0 to 1 with the vector field 0, negative y, z. Okay. Now, let's take a look at what this looks like. All right, I'm going to let's keep this, let's do this one a little bit bigger. Here's our vector field, the green and blue arrows, and there's our surface. Okay. Now, if I look at this, notice I see all these arrows coming into our surface, but not too many going out of the surface. So if I define outwards to be away from the surface, outside of the bowl, then I'm going to expect our flux integral to come out negative because it looks like there's more going into the bowl than coming out of the bowl. All right. I know it might be hard to see, but guys, all I did was I put in the vector field right here, and then I put in the function x squared plus y squared. I'll bring that back over here in a sec. So our function is z equals x squared plus y squared, and our vector field is 0, negative y, z. That's all well and good, but the formula I gave is for a parametrization. Well, this is actually the surface we parameterized last time. So one parameterization for our paraboloid, we could do u cosine of v, u sine of v, and then u squared gives it that parabolic look. Remember earlier when we didn't have the square, it made it a cone. And for this, we're going to want v to go between 0 and 2 pi. and u to go between 0 and 1, because we're only going up to a height of 1. Now, if I wasn't sure that this was the correct parameterization, I can test it. I put in the parameterization right here, exactly as I had it written. And notice I get the exact same surface. In fact, I can even turn this one off, and notice I got the exact same bowl that I had before. So you can use the Calc 3D plotter if you decide to parameterize a function to test and make sure your parameterization is working. You should get the same surface. Now, let's see, we're going to do our partials. We did these last time, so I'm going to go through them a little quicker this time. R sub u is cosine v sine v to u. R sub v is negative u sine v u cosine v 0. All right, next thing we need, cross product. Again, I've already got this one. This cross product should already be calculated on that sheet. And so once you do the cross product, and I think we did it last time as well, you should get 2u squared cosine v 2u squared sine v, and then let's see, we can factor out a sine squared cosine squared, so I think we just end up with a negative u. All right. Now, the integrand is going to come from the dot product of f and this. So now we're not finding the magnitude of this guy, but I do need to get my vector field in terms of r. So let's denote it like this, f of r, which means I have to put this in for x, y, and z. Well, x is 0. Y is u sine v, so negative u sine v, and z is u squared. So when I go to set up my flux integral, it's going to be the dot product of u, negative u sine v, u squared, dotted with 2u squared cosine v, 2u squared sine v, negative u. And again, our limits of integration are right here from our parameterization. So we could do du, dv, or the other way since they're all constants. 0 to 1, 0 to 2 pi. So this will pretty much give us our integral. Oops, sorry about that. So, oh, I don't know what. Ooh, something's up with my pen, guys. Hang on just a sec. Sorry. Okay. Hopefully that fixed it. Apologies, guys. All right. So if you do the dot product, remember that the dot product is multiplying corresponding components. Oops, that's the top of that pie. And then summing them up. So actually this first one works out kind of nice because 0 times 2u squared cosine v is 0. So just for a note, so let's just put 0 there. Here we're going to have a negative u times 2u squared. So that'll make it a minus 2u cubed. And then we've got a sine v times a sine v. So sine squared v. And then a u squared times a negative u squared. So minus a u cubed. And du dv. Okay, so we're just doing the cross product there. Now, again, for time's sake, I've already got this one calculated, and it comes out to be negative pi. Now, I want to show you guys a couple things about this, because we very easily could have gotten positive pi. All right. Now, one thing I'm going to mention it now, and I'll mention it again later. Sorry, I'm looking for our picture. This is this guy. All right. I want to mention this now, and I'll mention it again later. Now, in the previous problems, before we were dealing with vector fields, we were always finding the magnitude of the cross product. So this was a non-issue. Now, because we're looking at a normal vector, well, on any given surface, there are two normal vectors. You know, there'd be one coming out of the bowl and one coming into the bowl. So this is one possible normal vector, but the negative of that is another possible normal vector. So the question comes, how do you know which one to choose? Because both of them are normal vectors. I could have just as easily used negative 2u squared cosine v, negative 2u squared sine v positive u, and we would have gotten positive pi here. That would have been the only difference. Well, for a surface, you define what you want to be your positive normal vector. So in the case of this bowl, like I said, I wanted outward to be positive and inward to be negative. I know that this is the outward vector because look at along x. Along x is positive and along y it's positive. So going outwards. And the negative u is the dead giveaway. That's telling me that the z component of the normal vector is going down. So that would be the normal vector that is pointing out of this bowl. And that's why we're getting a negative pi for our flux integral, because as we saw in the vector field, let me expand that again. We have more vectors going into it and larger vectors going into it than we do coming out of it, right? We don't even see really too many vectors coming directly out of there. So, you know, one of the things you'll see in the homework is on a surface, the positive orientation will be given. Now we'll see later when we have a closed surface, by definition, outward is the positive and inward is the negative. But past that, if we just, if we had that plane that we saw earlier, we could really define either side, either direction to be the positive and the negative, and that will flip the sign on our integral. Okay. Most of the times in the problem, it'll be given unless you have a closed surface. When you have a closed surface, the convention is to have the outward be positive and the inward be negative. This was example 5. Questions at this point about this example, about the two normal vectors? All right, so let's talk a little bit more about, we talked about that. Let's talk a little bit more about the orientation. Every point on a surface has two normal vectors, right? One going on one direction of the surface, one going on the other. And the set we choose determines the orientation, and that's described as the positive orientation. Now, in order for a surface to be orientable, we need to be able to choose a normal vector in a way so that if it varies in a continuous way over the surface, when you return to the initial position, it still points in the same direction. So you can kind of see where this breaks down. We can look at the Mobius band. It's not orientable because if I pick an outward normal vector at one spot and then follow the surface around, so if we had a normal vector going upwards here, so if we picked a normal vector and said, okay, I'm going to pick a normal vector going upwards, and then we travel around the surface, right? Now all of a sudden we're behind there. So we're on the back side. Now when I come back over, I'm on the other side of the surface. So this is not an orientable surface. So we can't give it a positive and a negative orientation because of that flip-flop. So this only works for orientable surfaces. And I think, that it's easier to see the counterexample because most surfaces are orientable. All the ones we're going to do in here will be. Now, again, we're still doing surface integrals of vector fields, so we're still under that umbrella. And that's going to be the last thing we do. So we did surface area. We did surface integrals of a function over a surface. Now we're doing surface integrals over a vector field. So once again, the surface integral will be positive if the flow is in the same direction as our normal vector, negative if it's in opposite, and 0 if they're perpendicular. And again, how do we know which normal vector to use? Because any surface has two normal vectors at any given point. Well, if a surface is a closed boundary of some solid region, for example, like the surface of a sphere, well, then the positive orientation is the outward pointing vectors. So if it were a sphere, it'd be all the vectors pointing out of the sphere would be the normal vector we would use. And then the negative orientation would be coming into that surface. But that convention is only used for closed surfaces. So, the surface we did before didn't apply. I actually just chose to do outwards of that bowl as the positive orientation. But we could have just as easily called that the negative orientation because it was going down. And then our flux integral would have come out positive because we'd be going in the same direction as what we defined as the positive orientation. Okay. Like I said, don't think that that's going to be something that, oh my gosh, how am I going to choose the orientation? If it's just a surface, it'll be given to you. And if it's a closed bounded surface, like a sphere, or we're going to do a closed hemisphere here in a few examples, outward is automatically the positive. So you'll be given it, but I just want to let you know that. All right. Now on our previous example, we were given our vector field and our function in terms of x and y, and we were given our surface in terms of a function. So let's talk about doing a surface integral, a flux integral in that form. So if our surface is given by f of xy, well, then the normal vector is just going to come from the gradient. So if our surface is given by f of xy, we will call f of xy z, f of xy minus z. So this is similar to something we did back when we were back in, I think, module 3. Basically, what we're going to do is make our surface a level surface of a function of 3 variables by bringing the z over. And then our integral becomes the vector field dotted with the gradient. So we're going to try this with our previous example. So let's do this one. This is going to be example number 6. So our function was the paraboloid. X squared plus y squared. And I have to remind myself our vector field was 0, negative yz. All right, now we already know what the answer is to this one. We just need to make sure we get the same thing. So first thing we do is we turn our function to a function of 3 variables, which would be x squared plus y squared minus z. And now we find the gradient of f, which is the vector made up of our partials. So we have 2x, 2y, negative 1. Not a big surprise that last component's negative 1 because all we did was bring the z over. Now, we need to, now we're going to dot product f with the gradient. And we'll be integrating over our region, which will be our shadow region. And so f is 0, negative y, z. And guys, if you have any questions as I'm going through this, please, feel free to ask. Like I said, if all we get through are these examples, that's fine with me, as long as you get a chance to ask the questions that you guys have. We'll talk about our limits in the next step. Let's get the dot product out of the way first. So the dot product, nothing crazy going on there. It's just multiplying corresponding spot parts. 0 times 2x is 0, plus negative y times 2y, so minus 2y squared, and z times negative 1, so plus a negative z. All right. And this will simplify quite a bit to shoot. Actually, sorry, went too fast. This is a double integral, so we can't have z in there. So probably, I want to go back. I didn't need to. You can just change out the z later, and that's fine. But I'm going to change out the z here. I think that's better for notes purposes. Remember that z is x squared plus y squared. There was nothing wrong with what I had. You could have subbed in the x squared plus y squared at that last step. But I just want to change it here because I just don't want to have the z in there when I know I'm not going to integrate with respect to it. And our gradient, 2x, 2y, negative 1. So we're going to have the 0, we're going to have negative 2y squared. And then here, x squared plus y squared times a negative 1 gives a negative x squared plus y squared, which was the negative z we had earlier. And finally, distribute that negative. You can combine the y squared terms. You get negative 3y squared minus x squared. Now let's talk about our region of integration. So let me bring our guy back here. So we're back to x squared plus y squared. Again, same surface, so that's okay. I'm going to get rid of the vector field for right now because we don't need it for what we're doing. Remember that our limits of integration are the shadow region. So imagine a light coming straight down the z-axis and the shadow that would make. So our region is a circle of radius 1. So and right now we're in rectangular. So my limits need to be in terms of rectangular. So for a circle of radius 1, like I said, you're probably getting really used to these limits right now. Negative 1 minus x squared to square root of 1 minus x squared. That's if we wanted to do y first. So that bottom half of the circle to the top half. And then negative 1 to 1 dx. Now, this might be, to do this one by hand, we may decide to convert it to polar. All right. In fact, let's talk about converting it to polar. And this is back to Cooper's question from earlier, because if because it wouldn't be easiest. Because if we went to polar, this guy right here is only equal to r squared. We really only have to plug in for the y squared there. So we would have negative 2 r sine of theta squared minus r squared. And then now we do have to add in the r dr d theta, but our limits become a lot easier. 0 to 1, 0 to 2 pi. Now we have to add that r in. And guys, this one isn't as bad as it looks, because once you square this, that'll be an r squared. You'll distribute that r. You can do it piece by piece. It's actually not a very bad integral to do by hand. And you get the same negative pi that you did before. Now, again, I got with this integral, you're going to get negative pi. Same argument as before, because of the way the vector field relates to our surface. But again, there's two normal vectors. I used this one, but there is another normal vector that would have been the negative of the gradient. So how do we decide which one to use? Well, I wanted an outward orientation, which means I wanted a negative in the z direction, right? I wanted it going downwards because I wanted out of my bowl to be the positive direction. So that component right there is the one that's telling me this has the orientation that matches the orientation from before. Questions about that? How are we doing? We have one more example to go. So we'll get a little bit more practice with this. But just let me know if you got any questions about what we're going over. All right, let's do one more. Yeah, it's going to take some practice. This is a dense section, guys. There's a lot going on in this section. We've done surface area, we've done surface integrals of a function, and now we're doing surface integrals of a vector field. So there's three different things going on in this. They're all very closely related, as we're seeing, but there are three things going on. So it's going to feel like a lot. Now, as I always say, remember, you're not expected to memorize any of these formulas at all. You'll have your note cards for the proctored exam, so I don't want you to get caught up in that part. Where I want you to be is, how do we use them? All right, so last example we're going to do, this is example 7 from that. In case there was anybody who came in late, let me put this in chat one more time. So this has all the calculations. I did them all ahead of time in Maple, just so we wouldn't have to use up class time for it. All right, so calculate the flux of the vector field x, y, z squared over the surface, which is a hemisphere, given by x squared plus y squared plus z squared equals 1, and the disk x squared plus y squared is less than or equal to 1. This is a closed bounded region. This is a hemisphere with a disk on the bottom. So now we have a defined positive orientation. So we'll actually get to choose, choose which normal vector we want. All right. So this is going to be one where we definitely want to parameterize. Parameterization of a sphere we talked about last time. So the parameterization of a sphere really does come from the conversion formulas. So x is sine phi cosine theta. Y is sine phi sine theta. And z is cosine phi. And so what we would do is the same steps. We're going to take the partials of rho with respect to phi. Again, I've already got these calculated on the worksheet, so you guys have them there. Only because I just didn't want to use up class time for it. Cosine phi. These aren't that bad. The partials aren't that bad. The cross product is what gets messy. Cosine phi, sine theta, and then negative sine phi. And then you would find the partial with respect to theta. So you're going to have negative sine phi sine theta, sine phi cosine theta, and 0. So then we would do the cross product of these. R of phi cross with R of theta. Not a cross product I'm going to probably ever ask you guys to do by hand, so feel free to use technology for this one. So we end up with, I'm going to try and give you this simplified version. Sine square phi cosine theta, sine squared phi sine theta, and this ends up being, just cosine. It simplifies the cosine phi sine phi. If you're looking on the handout, you can factor out the cosine phi sine phi on that third component, and then the cosine squared plus sine squared ends up being 1. So it simplifies to that pretty nicely. All right, so that, now what we're doing, I should also mention, right now we're just doing the first half. We're just doing it for the hemisphere. We're going to have to do the disk separately. All right, so we'll do that in the next step. But this is one of our possible normal vectors. Remember, there's another normal vector that's negative of all these. Well, I want to have a positive orientation that is pointing outwards. And so I want the z component to point in the positive direction. So I want this component to be positive. So I'm going to use this one here, not the negative of it. Okay, because that's giving me that outward orientation. Now, as we go to set up our integral, we're going to be integrating with respect to phi and theta. And we do have to put in our transformation into our vector field. So F has to be rewritten in terms of R. Okay? So X is, now it actually works out pretty easy for this one because our vector field is X, Y, Z squared. So it's pretty much this vector, except the cosine of phi will be squared. But don't forget that part, that you have to transform your vector field to be in terms of your parametrization. And then we'll end up with a cosine squared phi. So that part there is our vector field in terms of our position vector or our parametrization. That's going to get dotted with the normal vector, which is sine squared of phi cosine theta, sine squared of phi sine theta, and then cosine phi sine phi, and of course I ran out of room. Let me see if I have any more space to write to the side. I don't. Shoot, wrote too big. Now we have to choose an order of integration, and it's going to come from our limits on theta and phi. So theta we know is going to go from 0 to 2 pi. Phi, we don't want to go all the way from 0 to pi because we only want the top half of the circle. So if we're going to do, let's say, d phi d theta, phi is going to go from 0 to pi over 2, and theta is going to go from 0 to 2 pi. So I'm not gonna do the dot product on this one for time's sake, but you multiply corresponding parts. It's actually not that bad. You get a sine cubed phi cosine squared theta. Actually, we got time. Let's go ahead and do it. 0 to 2 pi. That way I can write it in a method that'll actually fit. The cosine squared phi. The question is, where did this cosine squared phi come from? Remember that this parametrization has to be put into our vector field. So sine phi cosine theta goes in for x. Sine phi sine theta goes in for y. Cosine phi goes in for z, but then it gets squared. So that square is where that square came from. All right, let's see what we get. We get sine cubed phi cosine squared theta plus sine cubed phi sine squared theta plus cosine cubed phi sine phi d theta. So calculating that integral will give us the flux on the hemisphere, which is 11 pi over 6. So it came out positive. Let's take a look and see if we like it being positive. Remember, we used the normal vector that is outward. So that we would expect to see our vector field pointing outward. So here's our surface in our vector field. And that actually looks exactly what we have, right? We see all these vectors coming out of our surface, even at the top here. So it definitely looks like it's got a strong outward flux on this hemisphere part. So the fact that we got a positive, and actually a pretty good size positive, almost 2 pi, makes a lot of sense. Now, we do need to also calculate the flux that's on this disk, but that actually works out pretty nice because this disk is just the disk in the XY plane. So if I bring that back up, I don't have the disk on here, but that disk that would be the bottom of that would be the part that we're looking for. So we can actually just use the normal vector 0, 0, -1, because again, we want an outward flux. So we would want the z component pointing down. So this is, everything there is for the hemisphere. So now we're going to do, let's change the color. This is going to be for the disk. X squared plus y squared less than or equal to 1. We're going to use the normal vector 0, 0, -1. And we can actually dot this with our vector field. So F dotted with N. So we're going to dot together X, Y, Z squared with 0, 0, -1. And what ends up happening, we get a very trivial integrand because the only thing left is the negative Z squared. But look at what the value of Z is when we're in this disk. We're in the XY plane on this disk, so the value of Z is 0. So when we go to plug that in, let's see, we end up with the integral of R of 0 squared dA, which is 0, because we're in the plane Z equals 0. So there's actually no contribution to the flux through that bottom part, which, again, if we look at our image, look at the vectors around the bottom of our surface, right? The only ones we see are actually in the plane. So they're going parallel to the surface. So it actually makes sense that we're getting 0 flux on that bottom disk. So the total flux is the 11 pi over 6. Now, we're going to do this one again next week because one of our theorems works with closed bounded surfaces for flux integrals. So we're going to be able to check to make sure this 11 pi over 6 holds. The reason I wanted to do this one is because I just wanted to do one that was on a closed surface. And again, we're going to make a comparison next week when we do a similar one. Questions at this point, or about this example? Excuse me. Probably should ask that before we did it, but yeah, we had to calculate for something like this. We do have to, because we don't have one continuous surface. What we do is we do 2 separate surface integrals and add them together. We would do the same thing if our surface was made up of several planes or several different surfaces. When we look at the divergence theorem next week, we'll see another way of handling closed surfaces that works out really nice. But I wanted to do this one because it reinforces what we're doing in this section. And we'll see an easier way to do it when we have the divergence theorem. All right, so we made it through the 7 examples. Just one last thing I want to talk about. And it's the relationship between surface integrals and line integrals. We already knew there was a relationship because we saw it in Green's theorem, right? Green's theorem, there was the circulation form and the divergence form. The circulation form did a line integral, the divergence form did a flux integral. So basically, to do a line integral, we're taking up the components of the vector field that are tangent to our path. That's what the dr is telling us. For the surface integral, we're collecting all the parts that are normal. So they're very, very similar. And I want you to think of them as similar. I don't want you to think of them as 2 completely different things. The processes are very similar. So, with probably the biggest thing you'll notice is with the line integrals, because we could redefine our path in terms of one variable, in terms of one parameter, we had single variable integrals. Now, because we're looking at surfaces, they have to be parameterized in terms of 2 parameters. So we get double integrals. All right, guys, that is what I wanted to talk about today. I thank you for bearing with me on those 7 examples. I know it's a lot, but I think it is worth it to really dig into this section. So just to recap, we talked about surface area, we talked about surface integrals of a function, and then we talked about surface integrals of a vector field. And we did all 3 for both parameterized surfaces and surfaces given as a function. Okay. So, when you're making your note card for the exam, or when you're going in to do the homework, keep each of those things, keep them together because they're very, very closely related ideas, but label them so you know exactly what the problem's asking for, right? Did the problem you're working on, did it give you a function or did it give you a vector field? Is it looking for a surface area or surface integral? You want to identify those things because that's going to tell you what formula to use. So as you go through the homework on this section, be very, very cognizant of that. Why are you using which formula, and track that, because that'll be very helpful when it comes to the exam. So oh, this is a surface integral of a function, and it's given as a function. So I'm going to use this formula. Or this surface is parameterized, and I've got a vector field, so I'm looking at a flux integral, so I want to use this form. So be very cognizant of that as you guys go through the homework. All right, so we don't have time to break into groups today, but number 2 on the worksheet is a good one. If you want to try number 2 over the weekend and post your solution in chat before Tuesday next week, absolutely give you credit for it, okay? So something to think about, if you want a little bit of extra practice. So number 2, actually, you can do any of them from the worksheet. You post any of them from the worksheet, I'll give you credit for it. But number 2 is a good one to try because you do it both ways. And so it'll give you that practice of making sure you get the same answer both ways. All right, guys, that is what I wanted to talk about tonight. What kind of questions do you have? Let's start off with specific questions. Anything about this particular section or the examples? And after that, we got a few minutes left if we want to open it up for more general questions. But let's start. Give a couple minutes to see if there's any specific questions about this section. And as always, I'll post the video for this section tonight. All right, guys, what kind of general questions do you have? We have 2 sections left, Stokes' theorem and divergence theorem. Stokes' theorem is going to give a 2D way. It gives another way of doing line integrals. It's kind of a 3D version of Green's theorem. The divergence theorem, in a way, you guys already did it in 2D when you did Green's theorem. So we're just going to extend that into 3D. It's actually pretty easy to use. So we're going to my plan is to cover both those sections on Tuesday. And that way Thursday will be an open day, kind of like we did before the midterm. If you have questions, you can come in and ask them. But if you don't, if you want to use that day to work on take-home problems, study for another exam, et cetera, feel free. You have up until March 20th, 2 weeks from today, to take the final exam and turn in the take-home problems. You can take the exam anytime between now and then, but you still have till the 20th to turn in the take-home problems, regardless of when you take the exam. Okay? As always, guys, I encourage you to use technology on the take-home problems. If there are going to be some messy integrals on some of them, let Wolfram or Symbolab do the heavy lifting for you. Yeah, I mean, I don't want to say that the final is going to be rough. Remember that you have note cards to help with all the formulas. So what you guys need to focus on is how to use which one when. There is the review problems in the final review folder to help you get prepared. And, you know, the worksheets are also really good practice to help you prepare for the final. I'm not going to give you like the hardest problems on the proctored final. There's not enough time for it. And just like with the midterm, some of the problems are broken up into parts. Set up the integral for the first part, solve it for the second part. A couple of problems are about identifying whether or not you have a conservative vector field. And if you do, finding the potential function. So, and remember this exam, the final is going to focus only on modules 14 and 15. Obviously, there's topics like the gradient and stuff from the first 3 modules, but it is only going to focus on these 2 modules, which section-wise, number-wise, is about the same number of sections on the midterm, okay? And a lot of this stuff builds and is very similar. Like, you know, if you can do double integrals, that's basically what we were doing today for surface area. We were just doing different forms of double integrals. Next week, we'll do a couple triple integrals, but they're just triple integrals. So I don't want you to get too stressed out. You know, you still have 2 weeks to prepare, and we're starting to lighten up. Like I said, the sections next week are not on the proctored exam. So you have 14.1 through 14.8 and 15.1 through 15.8. Also, parametrized surfaces won't really be on the proctored exam. You know, I'm not going to have you parameterize the surface on the exam. I might give you a parameterized surface and have you do a surface integral, but you won't have to parameterize the surface on there. So it's not going to be as much as it may, it won't be everything from the second half because a couple of those sections won't be included. But leverage your note cards. Like I was saying, start to really think about why you're using which formula and when as you're going through the homework. I think that'll help you prepare to use your note cards when it comes to the exam. Any questions that you guys have? And if you don't, that's okay. You know, you can always email me questions. You know, you have the forum, you have the online tutoring, so plenty of opportunities to get help.